Hello, everyone. Today I'm going to present MTP, Transport for In-Network Computing, which is a collaboration among UT Austin, UIC, and Utah. Broadly speaking, in-network computing, or INC for short, is any idea that offloads functions that are often CPU-intensive onto NICs and switches to counter the slowdown of Moore's law. In the past, the offloaded functions are generally self-contained and common to many applications. Here we are showing an incomplete list of such offloads, from simple L3 functions like NAT to partial and full-fledged transport offloads to higher layer functions like compression and cryptography. Most applications can use at least a subset of them while doing I/O. But in recent years, we have seen a plethora of emerging ideas to offload L7 or application-specific functions. The most popular examples are key-value caches, RPC or HTTP load balancers, in-network aggregation, which accelerates or reduce for machine learning, as well as transaction acceleration for databases. In a shared data center where there are multiple applications or even tenants, these L7 offloads will coexist in the same network and can possibly share the same set of NICs and switches. This is an example of how we envision such a network will look like. There are two coexisting INC use cases, a key-value store, which offloads a cache, and the parameter server for all-reduce, which offloads two layers of in-network aggregation, or INA. To use the INA offloads, the ML worker's data should first pass through the L1 INA at the near-Tor switch and the L2 INA at the far-Tor switch. And similarly, a web server, for example, that wants to use the key-value store should issue the request towards the key-value cache, and in case of a cache miss, the request will go to the backend server. These are, in fact, overlay paths between the sender and receiver, with offloads being waypoints, so we call them pathlets. The pathlets, being L7, process messages instead of just packets, where a message such as an RPC can span multiple packets. Specifically, we have identified four types of operations. First, the pathlet may change the payload of the message, sometimes in a way that changes the length of the payload. For example, an HTTP load balancer can wish to insert a cookie to the HTTP header. Second, a pathlet can intercept the message, an example being an RPC load balancer that drops a request that it deems will anyway violate the SLO. Then there's reordering, where a pathlet can deliberately reorder the message. A pathlet that accelerates database transactions, for example, can do this to improve the server performance. And last but not least, messages can experience long and unpredictable delays at a pathlet. This can happen to some in-network aggregation pathlets, for example, where they cannot produce the result in time if there's a straggler. These operations happen between the application processes that run on different servers, and such communication is usually handled by the transport. Unfortunately, today's transports are not compatible. Mutation and intercept cause more or fewer data bytes to be delivered than sent, which breaks the ACK retransmit mechanism that achieves reliable delivery. Reordering leads to holes in the receive sequence, and protocol can see that as a signal of packet loss and retransmitted packets when they're actually not lost. Delaying can exceed the timeout length and cause spurious retransmission. It also causes fluctuations in congestion condition and delays the congestion signal, which makes the congestion control inaccurate. To make the matter worse, existing approaches are not generalizable. Running transport endpoint processing at pathlets, that is, the pathlet is both the receiver and then the sender, is not feasible with all INC hardware. Reconfigurable match action table is an example architecture that cannot run transport processing. Also, on the Wimpy core architecture, you can run the transport, but need a lot of cores to achieve the line rate. Many INC-enabled applications have proposed workarounds that are not widely applicable. Some have made existing transports work by relying on the specific insight about the pathlet processing. Others do not support all message operations. Therefore, we believe that there's a need for a novel transport design to natively support these message operations, and we propose the Message Transport Protocol, or MTP. MTP is the first transport to natively support the in-network message operations, hence the name, while providing two essential network transport layer services. First, MTP provides reliability, that is, recovering from the packet losses correctly and efficiently. And second, MTP provides congestion control to prevent congestion drops and achieve high utilization at bottleneck pathlets. MTP doesn't require transport-related state in the network, including the pathlets, which makes it easy for all types of INC hardware, especially those that are less capable to participate in MTP. Let's first go through the end-to-end transfer of a message to understand how MTP achieves reliable delivery with message operations. Say the sender asks MTP to send a message of 4092 bytes and the MTU is 4096 bytes. The MTP will send the message as a segment encapsulated in one packet. Say the pathlet performs mutation and somehow adds 8 bytes on the message. The pathlet will send 2 packets towards the sender naturally, and when both segments arrive, the receiver MTP acts the whole message, and the sender MTP then generates a completion for the application. The MTP sender in this protocol is passive in the sense that its only job is to act fully received messages and does not detect losses. The sender MTP detects losses with a timeout and retransmit the whole message when that timeout happens. If the pathlet decides to drop the message, it can just act the message as if the message was delivered. Message ordering is naturally supported because both the sender and receiver handle the segments and act for each message independently. That is to say, a message or act for a message doesn't have any implication on other messages. However, this design comes with a catch that message delaying is more challenging to handle because we use the sender-based timeout for loss recovery without assistance from packet or byte sequence number. This used to work in existing transports such as HOMA because the data center network has bounded RTTs, and RTO can be set relatively low. Whereas message delaying can incur unpredictable delays and cause false positives. If you set a longer RTO, you cannot quickly recover from losses. Therefore, our idea is to separate the fabric delay and pathlet processing delay and use different RTO lengths to account for them respectively. To achieve that, we designed a protocol where a pathlet can transmit special ACK packets to indicate that the message has entered or left the pathlet. Here's how it works. When the message leaves the sender starts a countdown of the fabric RTO, which is shorter to only account for the fabric delay. When the pathlet receives the message, it transmits a special ACK called pathlet RXACK, indicating the message is securely stored in the pathlet. And the sender switches to the pathlet RTO, which is longer to account for the pathlet's delay. Then, when the message leaves the pathlet will send the pathlet TXACK. The sender will again revert to the fabric RTO. The receiver will send the end-to-end ACK for the message when it has received the whole message. And if the message is dropped in the fabric somewhere, the sender can retransmit the message quickly with a shorter fabric RTO. We evaluate this idea with this setup. We have a software NIC that emulates a pathlet with either an exponential or bimodal processing time, averaging 100 microseconds to incur unpredictable delay, and the network link randomly drops, say, 1% of the packets. The sender issues 128 kilobyte messages in a closed loop. We use 2 setups. One is the baseline, which is only single RTO, and the other is our dual RTO design, where we vary the fabric RTO loosely. We vary the fabric RTO and loosely set the pathlet RTO to 4 milliseconds. Here's the result. We find that for both distributions, the dual RTO's design can achieve a much larger range of fabric RTO selection, where the goodput is near 100%. Also, on the right-hand side figure, you can see that for all fabric RTO selection above 400 microseconds, the dual RTO design incurs negligible spurious retransmissions, which prevents waste of link bandwidth. Next, we discuss congestion control. What is special about in-network computing is that pathlets now can be network bottlenecks, potentially running below the line rate, depending on the processing complexity and hardware resources. The challenge is that unlike the fabric that has constant link bandwidth and the known switch buffer sizes, the performance characteristics of the pathlets really depends on their implementation. So the operator can no longer empirically tune the congestion signals such as ECN threshold or target RTT and use them for the whole network. Also, end-to-end congestion signals can be delayed or later dropped. Therefore, we come up with a congestion control framework that allows pathlet-specific and early congestion feedbacks. We use one separate piece of congestion state, which can be a CWIN or rate for each pathlet to avoid conflicting signals from different pathlets. When a message arrives at the pathlet immediately sends out an early feedback in the form of a dedicated packet, which enables multi-bit encoding. This makes sure the congestion signal arrives at the sender and the congestion state can be updated in a timely manner, whether or not that pathlet delays the message or the message is later dropped. As an example of how this framework should be used, we quantize the queue occupancy of the pathlet into 8 bits and use the SWIP algorithm to consume the feedback and maintain the queue occupancy at a moderate level. We evaluate our congestion control with this setup. We configure the pathlet in our software NIC to incur random processing time from an exponential distribution. And there are 4 sender servers, each starting 2 closed-loop flows of messages towards the pathlet at a time. The left-hand side, we use a legacy congestion control framework that gives single-bit end-to-end ECM marking and use the canonical DC-TCP to consume the ECM marking. And on the right-hand side figure shows our example MTP congestion control. You can visually see that MTP converges more stably. We have also addressed several other issues. For example, one of the problems that our basic protocol cannot guarantee is exactly once delivery. That is provided by mainstream transports. And strawman solutions can lead to unbounded state size or cause head-of-line blocking, which does not go well with message reordering. We devised a scheme called virtual channel, which enables exactly once delivery of reordered messages with constant state size. Also, there might be more than one instance of a pathlet type available in the network, and we optimize MTP to dynamically leverage an alternative pathlet to achieve higher utilization and lower latency. We also did more evaluation, including an end-to-end benchmark with an existing INC-enabled application called Netcache, and we also did analysis showing the low cost of integrating MTP with offloads. Please read our paper for more details. To summarize, we abstracted the L7 offloads in an INC-enabled network as pathlets along overlay paths, and we identify the essential pathlet message operations, namely mutation, intercept, reordering, and delaying, and we argue that today's transports are incompatible. We have described MTP, which natively supports in-network message operations from pathlets, providing effective and efficient, reliable delivery and congestion control. And that concludes my talk today. Thank you for listening.